concerning large area, high quality glass cutting with femtosecond Bessel beams. I want to welcome you guys in our chat and all around the world in these days of a very special situation. And we are very happy to welcome you to let you know our recent research on Bessel beam-based cutting. So we are basically two partners. There's on the one hand side Cailabs, who developed the optical system and also provided the optical system to LZH. And on the other side, there's LZH, who did some experiments in the laboratory, and we want to show you our recent results. So in our agenda, we will first start with a short introduction to laser-based glass processing, and by myself, and a short introduction to Laser Center Hannover. Then Gwenn Pallier will continue with the Bessel beam generation and AXICON manufacturing.
Hi everybody. So I'm Gwenn from Cailabs, and I'm happy to be here with you.
And followed by the optical setup in the laboratory and the thin glass cutting experiments shown by Maik STEINBACH.
Hello everyone, my name is Maik. I'm working at LZH as a processing engineer.
Yes, so please don't leave this webinar afterwards. So please come back or stay tuned. We will show a small video to prepare the discussion, and afterwards we are very welcome you to the discussion round with your questions. You can already type your questions into the chat window, and we will come up with these later on to trying to answer them. So first of all, maybe and to do it a little bit more interactive, I want you to specify why are you here, and please maybe you can select the buttons. What's your interest at the moment over here, and mark the boxes. So let's continue with the presentation. And first of all, I want to give you a small introduction to our institution. So Laser Center Hannover is a non-university, non-profit research center for photonics and laser technology, founded in 1986 by 3 professors who were working on the one hand side, the optics, quantum optics, the material science, and thirdly, production engineering and machine tools. These 3 guys found this institute or organization to lay down the fundamentals in laser-matter interaction. So we are located in Hannover, that's in the mid of Germany, and we have around 180 people working at Laser Center Hannover, and 133 of them are scientists working on the fundamentals, but also for direct industrial applications. Most of our financial support comes from public funded projects in different fields, regional, national, and international, and also directly worked projects with industrial partners. So maybe you identified already that we want to bridge the fundamental research into industrial applications by working with scientists and engineers together at LZH. So we have 2 departments who are concentrating on the fundamentals, developing optical components and systems, and also laser sources. We have a big department for biomedical photonics, where our scientists work on biophotonics, laser medicine, or also biomedical engineering, for example, by establishing laser surgery. A very big part located for the engineering part is the optical production technologies. Here we are covering different materials and processes, for example, surface processes, generative processes of metals and non-metals, and also ultra-short pulsed, very micro-based processing. So in the department Maik and I are located in is the production and systems department. Here we are aiming for different materials and these kind of processing topics. For example, the composite materials group is working on the functionalization and structuring of repair preparation, efficient and low damage 3D and 2D cutting, but also welding and process monitoring. In the group of additive manufacturing, non-metals, we are concentrating on polymers, but also on multi-materials, where we combine different materials for multifunctional pieces, and are also covering a part that deals with micro additive manufacturing. So we also have the laser micromachining group, where Maik works for different topics. For example, the ultra-short pulsed laser-based microprocessing for surface functionalization, drilling, cutting, but also for thin film structuring and the integration of strain gauges on mechanical parts, for example. And the glass group I'm working in, we have different topics in our group. So very traditional is the marking, cutting, drilling topic. And in addition to that, we are also dealing with coating, coloring, functionalization. So the ablation of materials, but also the application of, for example, silver nanoparticles, microparticles, based on the one hand side, spray coating or also dip coating, and the thermal annealing afterwards. A third big topic is the welding and joining, where we use CO2 laser for the joining of different float glasses, or also the additive manufacturing, where we applied our welding process to a 3D printing approach. So let's have a closer look to the material glass and also the topic today, marking, cutting, and drilling. What are the advantages of glass? So glass is a material that is used for thousands of years, you can say, and applications can be found in a variety of fields. For example, used in displays for smartphones, in the automotive sector, or also smart homes. Used in electronics, in the OLED production or photovoltaics, architecture, of course, everybody knows this, and even more applications where you have extreme conditions such as high temperatures or also corrosive environments. So glass has some extraordinary properties, such as the transparency, the chemical inertness, and the thermal stability, so that you can use this material in extreme conditions, and of course in a lot of visual applications, because in the visual range it has a very high transparency and can be used in this kind of applications. So how can we use these glasses, this float glass, plain glass materials? We basically scrape and break them. This is a technology based 100 years ago by scribing with a mechanical wheel on the surface, and then to cut the whole piece afterwards by breaking. Nowadays, and some decades ago, also laser-based cutting techniques were established. And here we are aiming for different criteria. So on the one hand side, we have the quality criteria. When we think of substituting the conventional way by laser processes, we have to take care of chipping, induced stress, or also the surface roughness should be as comparable as possible. but for our processing technology, we need consider aspects such as geometrical ones, as the aspect ratio, curvature radii, or also the taper. And process-wise, we often have not only a one-step process, but also some pre- and post-processing steps. So if we now have a deeper look into the cutting topics, we can identify different technologies that are able to cut glass. So on the one hand side, we have the typical laser ablation techniques, where we use the laser for ablating, subtracting material layer by layer, I would say, and we have a very high flexibility within this technique, but there are also some disadvantages. So other techniques are also developed, such as scrap and break, quite comparable with the conventional scrap and breaking process. So first we induce local defects on the surface, and afterwards we can break them. And yes, for some years now, also volume modification based techniques are available. They are working with a very dense laser beam, where ultra short pulsed laser uses the nonlinear absorption inside the glass with a normally transparent, for the glass, transparent laser beam. But with these very fine beam shaping, we can use it for the modification of the glass inside the material to induce some kind of crack induced centers. And sometimes if you don't have a hardened glass or chemical treated glass, it will not cut by itself or separated by itself. Then of course we need a second step by a thermal induced separation. So today we will focus on the laser ablation, but with I think very high potential also for applications for the modification part, and therefore I want to give the voice to Gwenn for the continued introduction.
Hi. So let's see. Hi everybody. It's nice to be here with you. Thank you very much, Anne, for the kind introduction and for all the explanation about the glass cutting application. So my name is Gwenn, as I did say at the beginning of the webinar, and I am from Cailabs. And I will be explaining what Cailabs we bring to that collaboration for improvement of the glass cutting with femtosecond laser. So I will just start with a short introduction about the company, which you might not know already. So Cailabs, we are focused on beam shaping, and that's actually what we did bring to that collaboration. We are a young company. We were founded 6 years ago. We are in France, and over the years, we were focused on a unique technology, which is called MPLC, for multiplane light conversion. It's actually a technology pretty original of beam shaping. So basically, it can be applied to a lot of different areas. And in order to investigate all those areas, we have raised funds over the years. And last year, for example, we did raise 8 million euro, which actually was the biggest fundraise in an optical company for 2019. So just want to quickly mention that over the years, we've been always followed by Safran, who trusted us and with who we work actually quite a lot. So as I was saying, there are a lot of possible applications to MPLC, and I just want to quickly mention them. So over the years, we started by developing the telecommunication area first. And basically, we have 3 product lines for telecommunication. So Aruna is a product line for the improvement of local network, I would say local network rate. Then we have Proterus, which is actually more focused on the network of the future. It's more product for laboratories who are investigating what will be the the telecommunication in a few years or in a decade. And then the last product for telecommunication is STEINBACH, which is also focused on telecommunication, but a different telecommunication, which is free space communication. So it's telecommunication between the ground and the satellite. So I just see that there are some people who cannot hear me. So I'll do my best. I try to speak slow, and hopefully you will be able to follow. So I was saying, yeah. So it's you've probably heard that there are SpaceX, for example, who want to develop satellite constellation. So it means a lot of satellite all around the world, and it's actually very complicated to communicate between the ground and the satellite. So we have proved last year that actually our technology was really good for the improvement of this link. So quickly, we'll mention Cailabs inside. It's actually all other application. It means a lot of defense application, and we also have a lot of biology application. We have also custom project for specific people, specific customers. But today, we are here to talk about CANUNDA. So CANUNDA is our material processing product line, which I'm product line manager of. And it's for material processing in a large sense, meaning there are a lot of different applications actually inside CANUNDA. It can be laser beam welding for automotive. It can be also, for example, watchmaking or jewelry making with femtosecond laser. And it can also be glass cutting with our CANUNDA-AXICON product. So as you can see, there is a lot of area of interest in common with LZH, and hopefully we will collaborate on other topics as well. But today we are here to talk about glass cutting. So how to cut glass? Arndt did explain that quite well already, and you could see on his scheme that one of the interesting way to cut glass is to drill holes through the whole thickness of the glass. So a good way to do that with a laser is to have really high aspect ratio beams. It means that you want to have a really long beam which will show quite small widths. So the classical way to do that is to use an AXICON. So basically here you have a transmissive AXICON. You have the beam coming in on this side and coming out of the AXICON through this conical plane. So the beam will have a conical face, and when both beams will meet, they will interfere, and this interference will actually create this very intense beam and very long beam. So you have to imagine, of course, that all this is in a 3 dimension. So these AXICON, they are the best way to generate this really high aspect ratio, and they are perfect for drilling through glass. But the thing is that this classical way of generating Bessel beams with transmissive AXICON has limitations. I would say that basically you have 2 main limitations. The first limitation is the blunt tip. So the way you manufacture these transmissive AXICON, you always have a round tip at the top of the AXICON, and then you have a part of your beam which is getting out with a conical face, and you have a part of the beam which is getting out with a spherical face, a small part of the beam, but still a part of the beam. And both these 2 parts of beams will interfere as well, I would say, and they will create oscillation. So oscillation, you can see them along the optical axis over there. So why it's actually pretty bad? It means that either you will be below the ablation threshold somehow in some areas, and you will not ablate the glass. Either you will be above the ablation threshold everywhere, but where you have the high intensity, you will be too much above this threshold, and you may create damage in the glass. So that's actually one big drawback. The other drawbacks is that we are using femtosecond lasers. So because they are femtosecond, they have to have a broad spectrum. So broad spectrum doesn't like glass. When you go through glass, all wavelengths are seeing a different index. So you cannot actually keep the pulse duration with a transparent AXICON. Then if the AXICON heats up, because you are actually sending quite a lot of energy inside it, well, the index will change, and then the different wavelengths will again see another glass index. So all these are quite limiting for the Bessel beam generation for high-quality glass cutting. What we have developed in Cailabs is another way to generate those Bessel beams with a reflective AXICON of high quality. So I will just quickly explain how it works. You have your input beam getting on the AXICON, then the output is with an off-axis angle, then the setup are easier to make. You have your Bessel beam just there when both beams interfere, and on the far field you have a ring, actually similarly to transmissive AXICON. But it's reflective, so it means you have really low losses. You can handle really high power, and you don't have any impact on the spectrum, on no chromatic dispersion, and the pulse, the femtosecond pulses are preserved even for really short pulses. So those AXICON, they are really perfect for ultra-short pulse laser processing. I will go quick on that, but it's important to know and to understand that there are a lot of possible different Bessel beams with an AXICON. And finding out the right parameters was actually a tough job that LZH did and that we helped them to do. When you have an AXICON and you change the wavelengths, you are actually changing the Bessel beam. When you change the input waist, meaning the input beam diameter, you are again changing the width and the depth of focus of the Bessel beam. And then at the end, you can also change the AXICON angle. We have a lot of different possible AXICON angle, and it's changing again all the parameters. When you change the beam dimension, of course, you change also the intensity at the maximum point inside the interference area. So all this is a little bit different to tune, but it can also be seen as a really good opportunity. And there you can always find a configuration to meet your exact need for your material processing. So those Bessel beams that we've been generated with reflective AXICON, they are actually the Bessel beams with the best quality that we have found actually on literature. And you can see that first on that slide, because actually here in red, you have the curve, the theoretical curve of a Bessel beam. And you can see in black that you have what you get with our AXICON. It's extremely close to the theoretical curve. In blue, you have what you get with actually a quite good quality transmissive AXICON, and you have a lot of oscillations, which are pretty bad for the processing, as I just said. Just want to mention that here you have a little bit difference between the theory and the actual measurement. It's not because of the AXICON, it's actually because of the laser beam. As most of you probably know, it's pretty classical with femtosecond beams that they have kind of wings at the edge of the Gaussian beam, and those wings actually, they create this little difference. So we were pretty happy of the quality of the generated beam. And this cannot be seen with a transmissive AXICON. So another point which is pretty important to know about those reflective AXICON is all the possible setup that you have with them. So you have a standard setup with the AXICON being used, I would say, alone. And you have the processing area here. And you also can use them with a microscope objective. That's also a quite nice setup because with this, okay. Okay, so I don't know if you can hear me or not. Maybe Tatiana, you can let me know if it's good. I will just wait for a minute. Okay, so if Tatiana can hear me, I would say that everybody's hearing me. So I will carry on. Was I off for a long time or not? I don't know. Well, anyway, these are the standard setup that you can have. And I was mentioning that the microscope objective actually are quite good because you can generate very small Bessel beams. At last, you have this setup which will be detailed later on by Maik. And it's actually a very unique setup as well. And this is also the first time that it was possible to use that kind of setup with a Bessel beam, because you have the F theta, but we went actually through a galvo scanner as well, and that was pretty unique. So this is also why our AXICON, they have the best possible quality, because the stability enabled that. And I also want to end my presentation by saying that if you have at home, when you are doing home office, femtosecond laser and a galvo scanner, well, then you can reproduce part of that at least, because now the CANUNDA-AXICON, they are available online. You can buy them off the shelf on Edmund Optics. So I invite all of you to just buy one and try to repeat all that on your own. So after that small part about the AXICON, I will leave the floor to Maik to explain all the process results that we've got with that setup and with LZH. Maik, are you with us?
Yes, thanks a lot, Gwen. I will continue. Okay, so hello again. The next few slides will be about the tests that we did at the lab at LZH. We have two laser sources available for our Bessel beam tests. You can see both of them in the picture on the right. The first laser is a coherent Monaco. The pulse duration is adjustable between 10 seconds and 350, between 10 picoseconds and 350 femtoseconds. The wavelength is 1035 nanometers. Maximum repetition rate is 50 megahertz with an average power of 60 watts. Maximum pulse energy is 80 microjoules at 750 kilohertz. The second laser is an amplitude S-pulse, HP, with a pulse duration of 600 femtoseconds. Wavelength is 1030 nanometers. Repetition rate ranges between 1 kilohertz and 100 kilohertz with an average power of 4 watts. The maximum pulse energy of the S-pulse is 800 microjoules at 1 kilohertz. With these two systems, we can test a large variety of laser parameters and develop laser processes for industrial and scientific applications. Here you can see the Bessel beam setup in our lab. I will try to show my mouse pointer. I hope everyone can see it. So, coming from the pinhole at the bottom, the laser goes to the upper left mirror and then reaches the first telescope, that's the numbers 1 and 2. This telescope has a magnification of 0.2, with the focal length of lens 1 being 100 millimeters and the focal length of lens 2 being 20 millimeters. There is a 30-degree mirror that reflects the laser beam towards the AXICON, which is here. The incident angle of the AXICON is 15 degrees. After the AXICON, we have the second telescope, with lens 3 having a focal length of 200 millimeters. You cannot see lens 4 in the setup because it's right under the laser scanner, which is a black box on the right side. This means that we adjusted the setup so that the galvo scanner with its mirrors is in between the second telescope. Lens 4 is a telecentric f-theta lens with a focal length of 100 millimeters. So the magnification of the telescope 2 is 0.5. By adjusting the two telescopes, the Bessel beam can be modified, so a lot of process optimization can be done here with regard to the substrate that you want to process. After setting everything up, we monitored the Bessel beam. We used this Bioicon beam viewer for that. With the laser scanner, we moved the beam across the scan field. We could measure a homogeneous intensity distribution throughout the scan field. We also moved the camera along the z-axis to measure the beam profile in that direction. By playing around with both telescopes, we could generate Bessel beam length between 2 millimeters and 2 centimeters. We also did some material processing on thin glass. The glass shown here is a shot glass with a thickness of 50 microns. We processed the Cailabs and LZH logo with a single crossing. If you have a closer look at the LZH logo on the right side with a STM picture, you can see the bars of the LZH logo being intact and showing a good processing quality. We also tried to drill some holes with the Bessel beam. When we had a look at the SEM picture that you can see here, we would see a large damaged area next to the drilled hole. And if you compare that with the picture below, you could argue that the secondary rings of the Bessel beam also damaged the material. Probably the chosen pulse energy was too high. It's a very difficult task to find the correct processing parameters with a Bessel beam because the intensity distribution is very different to a Gaussian beam. A lot of testing is needed here to get some experience and the required knowledge for material processing with femtosecond Bessel beams. Okay, so here's a small conclusion. In this webinar, we showed that generating femtosecond Bessel beams in reflection is possible with a CANUNDA-AXICON. The reflective AXICON was combined with a laser scanner for the processing, for fast processing possibilities. The Bessel beam shape can be modified towards your needs by adjusting the telescope setups. And processing tests showed that it's not so simple to find the correct laser and Bessel beam parameters in order to get a very good quality. More experience and tests are needed. LZH and Cailabs will continue their cooperation on these topics besides other planned projects. And now we have prepared a video for you that we would like to show right now. After the video, we will try to answer all your questions. Thanks a lot for your attention.
Hi all, so this is just a short video about the work we did together. So take this minute of video to have a look at what we did, and you may also use it to write the question you had about the AXICON, about all the technology that we could provide, about what LZH is doing. Do not hesitate to ask questions, and we will try to find some time to answer all of them just after the video. So hope you will enjoy the video.
So thank you very much for your attention so far. I hope you enjoyed the presentation, and now we are open for questions from your side. And yeah, we try to collect all the questions you dropped down so far. So we will go through part by part and we'll try to answer them right after one to another. So the first question was, what is the shape of reflective AXICON? Same as glass one? So maybe this question can be answered by Gwenn perfectly.
Hi, yeah, definitely I can answer that. So yes, basically, it's somehow the same as the glass one, because it's conical. So we also did a conical shape, but instead of being convex, it's concave. Or if you want to have a diverging beam, then instead of being concave, it will be convex. Just meaning that you're digging instead of having it, I would say, at the outside of the AXICON. But basically, it is also a conical part. Hope it answers your question.
Okay, so yes, just drop down another question if you have if you need further information. So there was a second question, also by Ahmad Ode, number one, connected to this topic. Is it curved in the center?
It's actually a pretty good question. So basically, we cannot make magics. It's always you always end up having a curved area. The thing that our curved area, based on the manufacturing capabilities that we have, is actually way smaller than the one of the transmissive AXICON. We are talking about a factor of 10 or something like that. But I cannot say the figure. So if you want to have more information on that, do not hesitate, send me an email, and I will find out what the exact figure for that is. But basically, you can see from the profile that we did show that you have hardly no oscillation. So it means that you have hardly no curved area at the tip of the AXICON.
Okay, hopefully this answers your question. There's another question concerning the laser setup. So, or maybe we will first go to this question. What is the sensitivity of AXICON to the laser fluctuation? Is it a daily control, and how? So maybe this deal scopes for the experimental setup. Maik, can you tell us something about this?
Yes, so we did not see any fluctuations when we set everything up. So the setup is very difficult and it took a lot of time. But once we had everything set up correctly, we could not see any fluctuations. Beam looked fine for a longer period of time.
Mm-hmm. Okay, and then there's a question concerning the laser source. Which kind of architecture is Monaco laser? A la fiber, solid state, hybrid, etc.?
Yeah, it's an ultra short pulse fiber laser.
Mm-hmm. Okay, so maybe we can go to the next question. For thin glass cutting, are there differences between Gaussian and Bessel, especially in terms of cutting quality? So I think what the results you could see so far are comparable with the Gaussian beam, maybe not that optimized. So there's some more work left for better edge quality, and also the heat affected zone may be caused by the higher orders of the material of the laser beam needs some more optimization. So we want to come to the same quality level. Of course, I think with a very good optimized Gaussian beam, you see at the moment advantages, but of course we're working on this, and yeah, we are at the beginning of this process. So then we have a question: Is the result in question of defects comparable to classical filamentation modification with normal AXICON and microscope lens? If not, where's the main difference? So the question is, can we realize the defects inside the material with this kind of setup? I think to give you an answer at this moment, this has to be tested in the future. And I think there's also some more research needed for this. Okay, one question to Maik maybe. How is the diameter of the Bessel beam in the scanner setup?
The diameter of the Bessel beam was around 40 micrometers for the central point, but this depends on the telescope optics. So if we change the telescopes, we can arrange different diameters of the Bessel beam, and you can do a lot of different diameters. So it depends on what you need and what diameters you want, and I'm pretty confident that you can get the diameters you want.
Okay, thank you, Maik. I hope this answers the question of Tim Hesse. And let's go on. Ahmad Odi, number one, has another one. What kind of scanning strategies can be used with the AXICON? Is there something an overlap or something like that?
Well, I think there are a lot of scanning strategies that can be tested. So we tried to cut in a single cross. Also for drilling, it's interesting to not use other. I mean, with the beam, you do something like percussion drilling. That's not necessary with the Bessel beam because you ablate the material everywhere in the volume. So I think there are some new strategies with the Bessel beam that can evolve. So that might be even better than the strategies that we have with a Gaussian beam currently.
Okay, and there's another question by Bill Holtkamp. What are the limitations to the length that can be modified in a single pass? What is the typical diameter of the Bessel beam?
Okay, so as I said, the typical diameter of the Bessel beam varies depending on what kind of telescope optics you use and what kind of f-theta objectives you use. Typical can be 50 microns. It can be larger, it can be smaller. I think it will be very difficult to get to below 10 microns. The limitations. Yeah.
Sorry, Mike. Please carry on. I will just add something afterward.
Okay. So the limitations to the length. It is the pulse energy that we use. So if we use the Bessel beam, the laser intensity is not on an area, but it's more distributed over volume. So if you compare the intensity that you use with a Gaussian beam, you need much higher intensity in order to process your material. So I think the limitations that we currently have is maybe pulse energy, repetition rate, or laser power.
And just one thing to add, it is an interesting question because indeed there are a lot of different possibilities for the Bessel beam, as you were saying, depending on the setup. Just want to say that in the past we did try with a pretty different setup with a microscope objective to generate small Bessel beams, and we managed to get down to 100 nanometers. And on the other side, I just want to say that if you want to play around, we ended up that thinking that it's very difficult to always answer that question that we always have with AXICON. And we have now a calculator online. You can play around. You pick up an AXICON. You can change the setup. You have a little bit of choice of configuration. You have different microscope configuration and different f-theta configuration, which are kind of matching what most people are using, or at least it will give you a first ideas. And you will see that you have Bessel beams from really a huge range of width and of depth of field, depending on the setup. That's it for me.
Okay.
I think there's one more question.
Yes, one more question. Did you try to cut crystalline materials? So I think so far it was only the glass material, but I can imagine that also it will also work with other class of materials. So this technique is based on an ablating technique. So it evaporates and destroys the material. It's not a filamentation or something like that, but I think there's some kind of that there is potential to use this for some kind of filamentation process. Okay, so I think we answered most of the questions, or all of them. And with this, we really want to thank you for your attention following this webinar. I think there will some further webinars, especially at Cailabs, but maybe also at LZH. So we were happy if you follow our websites for further information. After this webinar, you will be also redirected to the information bundle. And with these words, I want to and we want to thank you for your attention, and see you soon.
Bye.
Bye, bye. And just to answer the very last question, on our website, www.cailabs.com, or send me an email. See you. Thank you.
Yes.
Bye-bye.
Bye.